This is tutorial 10th of Cadence Virtuoso IC615. In this tutorial, I'll be showing how to do the corner analysis of our design. Corner analysis is used to find the process inaccuracies and temperature and other process variations, parameter variations. This simulation, in this simulation, we see the effect of process and environmental variations on our design. And these process corners are defined on the basis of the speed of each transistor interconnects present in our circuit. And like for example, there are 5 types of process corners defined in our this Cadence Virtuoso, which we use. One is FF. The FF stands for fast pass, when both PMOS and NMOS behave as fast transistors, and similarly there is SS. Both behave as slow, and there is fast PMOS, slow NMOS, and fast NMOS, slow PMOS. And one is typical. Most of the simulations which I had done so far, I had done consider condition typical. Typical is, it's like the ideal case where we are having the environmental, everything is according to our it's ideal case. There is no variation in everything behaving perfectly. But when we go with our design for fabrication, it is important to perform this analysis to verify whether our design will meet certain requirements when it is put in that practical in some application where different types of surroundings may encounter that circuit, like atmospheric moisture may affect this, or a different density, like doping may affect the, if you see different amplifier, doping may affect mismatch and all that. So in this we predict how much variation is it, and we have to make sure that is it within our own required requirements. So for doing the process corner analysis, so I'm going to use the same inverter which we have been using so far, and the state I have saved for this, I'll be using that one only. So for doing process corner, we have to go for this ADEXL. Instead of ADL, we have to go for ADEXL. ADEXL is the advanced version of ADL. In ADEXL, there are these extra features of doing parallel simulations. Like we can do simulations in parallel, and we can take it's like a sometimes it's advanced version of this parametric analysis we do, and we can do in bulk. We can take like 100 samples, and we can see the effect on them, and like that. We'll go in detail, and if you want to see the documentation about ADXL, it's in help. So I launch this ADXL and create new view. Okay, so yes, I'm going to use it for inverter. Oh, here it shows open in new tab, current tab, new window. I'll just keep it new tab so that I can shuffle between two. Okay, it's showing it already exists. I'll overwrite it. Okay, so there is some introduction about this ADXL. You can read also here. And now here the first thing is test. Test is the the state I have saved for this. Like for example, I had done some DC simulation. I want to do some corner analysis or Monte Carlo or something for that. So I can add it here, whichever tests I have saved. So first let's do it. I'll click it, and it will show me this two windows will come up, and it will show me the this cell view for which I want to load that state. So it is inverter. Okay, yes, just do okay. And this AD window is coming, ADL XL window. So here I load that state which I have saved. So if there are 2-3 states I have saved, so I can, according to my own this requirement, I load that state. So there is only one state, I will be loading this one. Okay, I can do this simple simulation here also. There is no need to go for ADL. For example, if it's like this, I'll just run it. So if you drag this is the run option. So if I run it, so yeah, see, if I plot it, this is for plot, and it will show me this result of inverter. Okay, so now what next? This is the global variable. If I define some variables, I can click them, since I have one is already there. Like for example, in case of Monte Carlo simulation, I had to define the sigma value. I'll be in upcoming tutors, I'll be talking about this Monte Carlo simulation also. So I had to define the sigma value, or I can put temperature as a variable like that, and similarly here parameters, and this is the corner while we define our, so for now, and this is the brief thing. And if you go here, there are different types of simulation if you want, like Monte Carlo. I want to global optimization, yield, I'll go one by one to everyone, and mostly I'll use only three types of simulations for my purpose. One is one is this corner analysis, one is Monte Carlo, and this yield I'll see, and this worst case. Worst case is like it's very important to do when we go for this fabrication, because we want to see in worst environment how our circuit is going to behave. So this is one better. It's newly introduced by Cadence. So okay, for now I'll go for corner analysis. So for now it's nominal, that is it's showing here, it's typical, no other corner is here. So I'm going to add those corners here. Click here, click to add, and this window will come here. Now I can see the variation with temperature. So first of all, okay, let's go for another corner. This is for add corner, new corner. So I'll just click it here. So it's coming here, one corner is coming, and the first thing is design variable, it's x. So x I am varying from 0 to 1 point, comma 1.8. okay, so I am varying 0 to 1.8. okay, that's it. And now I have to add the model files here for this. See, for every this technology, this process corner files will be there, like these are model files. You go same, you go here, click on that model file, and just go here, just double click here, and you go to the model and Spectre and Monte Carlo. For UMC it's like this. If you see for PDK, GPDK is here. Mostly some IBM, or some people are using some other. It will be in Spice, or whichever if you are in Spectre, it will be there somewhere. So one thing you have to notice, you have to see this .lib.scs, not .mdl.sl. It should be .lib.sl like this. And if you see there are two corner files. One is, this is for 3.3 transistor, this is for 1.8 transistor. Since I'm using 1.8 transistor for making, so I'll select this one. So that's it. Just open it. Okay. So I edit. Now I define my corners. Which corners I mean? Generally, if you see, we use only we only check our circuit on three process corners. One is typical, one is fast, one is slow. But for this sake of lesson, I'll show all corners. So just click on here, double click. So if you see here, all the things are defined, which type you want. So I'll just click fast, again go here, then I'll take this fast N. If you see FNSP, that is fast N MOS, slow P MOS. Similarly, if I go down, it will be SNFP, slow N MOS, fast P MOS. Then I'll go for this slow, and I'll go for this typical. Okay. So these are the 5 process corners which we define, which are used to define to see the behavior of our circuit at in certain conditions, when our transfer will behave fast or slow, or interconnects like that. Okay, so once this is done, just press OK and run it. So it will be running, and I think 11. Okay. So this is the feature of this ADEXL. See, if you see here, this is not possible in ADL. I can show you there. I will show you at the end. I can do this process corner there also, but I will do one by one. Like I will do one time for FF, then one time for slow, then one time for FNSP, then one time for like that. But here I can do all. I can define once, and it will do at once. Okay. So we will be seeing the effect of the transfer speed on our circuit, like how it's behaving at fast, slow, fast, and fast, slow, FS and SF, and typical. So these are the different plots. I can individually plot them, or I'll just go here. It will plot all things. Okay. So now what we are seeing here is, okay, just this is our what I will do, I'll copy it to new window. Okay. Okay. So if you see here, This is our VI characteristics curve, and I'll just click here output, and I'll just what I'll do. Okay, I'm not able to see it here, but I think it should show. Wait. Okay, this is for yeah. What I will do, if it's not showing it, I'll just double click on that. It will show me here. Okay, this is for FNSP. If you see here, it should show. I don't know why it's not showing. What I will do, what I will do, this thing, I'll just no, yeah, we'll see like that. It shows. I don't know why it's not showing. Okay, yeah. If you see here, now this is the rise time. Okay, if you see here, this is for fast, this is for slow, NMOS, fast PMOS, and this is for typical or nominal, and this is for again typical, and this is for fast NMOS, slow PMOS, and this is for slow. So if you can see, when our transistor will behave as slow, the speed will be less, and the rise time and fall time, it will definitely increase. And if you see here also, it will be more. Okay. So similarly, if you see here also, there will be some variation also here. If you see here, and it will be. So this is how we do process this corner simulation, and okay, this is it. So yeah, I was talking about if we do in ADL, what is the difference between ADE and ADEXL? So yes, if I launch this ADL, now here if I want to do process corner, some people I have seen they will be doing like this. So what I'll do here then, this, for example, okay, I'm using this, let's say I'm using this transistor, this one. Okay, so for here I have to define it like, okay, I defined it slow. Now I press OK, and now whatever simulation I'll be doing, it will be based on only slow. And then again I have to go again back, change the setting to fast, then do this. It is time consuming, and this I can't see the difference here also. So it's better to, that is the advantage of ADEXL. Thank you.